So thank you so much, Aditya, for inviting me to McGill. This is my first visit at McGill. I'm very, very impressed and excited to be here. I'll be here for the rest of the week as well until Friday. So if you are interested in chatting with me, even tomorrow or day after, feel free to let me know. And I'm happy to meet all the way until Friday evening. So this is the work that came out of our various projects that we have done since 2018. And I think the common theme across the different strands of work that we have done in our group essentially is stemming from this issue of solving for optimal control problems in a vehicle setting, or autonomous vehicle setting. But I think the theoretical tools that we have developed is more general and therefore applicable in a wide variety of situations. And so today I'm going to be giving a talk on, like, motivated by connected autonomous vehicle applications. I'm going to talk about theoretical work that we have done. But we are not going to go into the implementation details that was taken care of by my colleagues in the mechanical engineering department. But we did implement some of these algorithms that I'm going to talk about on actual autonomous vehicles testbed at OSU. So let's start with the motivation. Why are we interested in perturbation theory for dynamic systems and specifically dynamic programs? So if you look at many high-dimensional dynamical systems, such as humanoid robots, autonomous vehicles, power plants, HVAC systems, and battery management systems, you have very high-dimensional state spaces, you have very high-dimensional action spaces. But the key thing here is that the environment in which these systems are acting are continuously changing. So if you think about it from a dynamical systems perspective, many a times you have, let's consider the case of a robot. You have a robot which is navigating in an uncertain environment, and there are people walking around, there are vehicles, or there are other objects that are moving around. So their system, their environment is continuously changing. And so what that leads to is every 1 second or every 2 seconds, the dynamic program that they are trying to solve completely changes. I mean, maybe not completely changes, but changes slightly from one time step to another. The problem is that dynamic program is a very, very compute intensive activity. So at every point of time, if you have to resolve the entire dynamic program for the new situation, for the new constraints, it becomes computationally prohibitive. Okay. So the question that we asked ourselves when it was posed to us back in 2018 is, how can we solve these problems efficiently, given that we already know the optimal solution of the current dynamic program, and then the next dynamic program 1 second later is slightly different than what the current program is. And so how do we solve that problem?
I mean, the robot and the autonomous vehicles are different from the next three, right? Because there you have the configuration changes because a new robot comes in or something, someone else leaves or something.
Yeah.
There you have also event-driven changes, which are more discontinuous.
That's right.
Whereas these are much more, your continuous but changing thing applies more for these.
So like
unless something fails or something.
No, building HVAC was also changing. So for instance, there were 30 people in the room like 5 minutes ago, and now there are like 7 people or 8 people in the room. So even in building HVAC, the outside temperature is changing every minute. So a lot of these things eventually ends up affecting the different set points and different actions that the things have to take. In power plant also, if you are doing frequency regulations and if you're doing generation, then the demand is fluctuating and you need to be aware of that. So in all these cases, there are some small things perturbing every few seconds.
I was saying the robot and autonomous vehicle perturbations are probably more discontinuous.
I understand why you were saying discontinuous, but actually it's
event-driven in some sense.
Right. It is definitely event-driven, but it's not that discontinuous. Certainly, you could have a few extra constraints, but it's not like everything is changing quite significantly at every 1 second interval. So for instance, when you are driving a car on the road, and I'll talk about it in a bit, when you're driving a car on the road, and if a car comes into your lane, that's a sudden change in your constraint, but it's only one constraint that changes, which is a velocity constraint, but the dynamical equation of the vehicle doesn't change. So perturbations are ubiquitous, as we all know. There are short-term perturbations, that is what we are talking about. So you could have a situation where you're driving on a mountain, and so the slope of the mountain or the traffic on the road is changing in very short durations, within 5 seconds, within 10 seconds, or a minute basis. You could have a crash where things change very significantly in a matter of a few milliseconds or a few seconds. You can have medium-term changes. So for instance, your oil degrades if you're driving an ICE vehicle, internal combustion engine vehicle, then your oil and your fluid would degrade over a period of 4 to 5 months, 6 months. Weather changes over a period of months. And then there are certainly long-term degradation which happens, which is over the period of years. And while our group has worked on all these three different types of perturbations, today's talk is mostly about short-term perturbations, while we are not going to be talking about medium-term and long-term perturbation in the system. So this was the problem given to us back in 2017, I think, which was to, so this was the vehicle testbed. It is sponsored by Delphi Technologies and a bunch of other companies, as well as ARPA-E. And you can see the Ohio State logo as well. So actually this vehicle is in Ohio State, it's Ohio State's property. So the goal for this particular vehicle was, so this had a lot of instrumentation to be able to get information from the roadside unit, get information from the traffic lights, and all of that stuff. And so if you, I don't know how many of you remember, but in 2017, there were supposed to be autonomous vehicles and connected vehicles by 2020. We are in 2026, we don't have autonomy. I mean, we have some autonomy somewhere in the world, but we don't quite have it everywhere. But that was the promise in 2017. And so people were thinking about what happens when all the roadside units, all the traffic lights, all the vehicles become connected, which is going to happen in 3 years at that time. And so we want to reduce the total fuel consumption of the vehicle. So that was the idea. So how do you reduce the fuel consumption of such a vehicle? So because you have look-ahead information, you know when the traffic signal is going to go red, when it's going to go green, when it's going to go yellow. You're able to sense the environment, you know when the pedestrians are going to cross the road. You're able to sense all of that information. Now, once you have that information, you set up a dynamic program, and can you use all this information to reduce the fuel consumption? And the goal was to reduce the fuel consumption by about 20%. In a connected autonomous vehicle. And essentially the way this worked was you collect all that information from various sensors like radars, camera, and whatnot. You process all that information, you set up the dynamic program. And at every 200 milliseconds, the dynamic program is going to be not recomputed, but it will be redone. Like the entire dynamic program will be formulated every 200 milliseconds based on the information that's coming in from all different sensors. And then the next phase, this was the first phase of the project. The second phase of the project said, okay, now that we have optimized the vehicle speed, let's try to optimize the heating, ventilation, and air conditioning system within the vehicle using this look-ahead information. So now you have a HVAC system, you have a compressor, you have a evaporator, you have the fluid, the refrigerant moving through that compressor and evaporator loop. How can I use this information that the vehicle is going at a certain velocity and there is a red light, there is a green light, whatever? How can you use all that information to improve the HVAC energy consumption? And there the DP was perturbed every 5 seconds. So as you get more information, you can.
This perturbation is, I mean, I would have imagined, at least for something like the fuel economy, the perturbation is happening continuously, but you are only making change in your DP every 200 milliseconds or whatever. So
for the safety purposes.
Yeah, but there would be some period of time where you are working with or rather like almost all the time you're working with non-optimal policies, right? When you say
or near optimal, yeah.
Okay, so DP is perturbed is more like the DP is you're recomputing a policy those milliseconds, not that the environment is changing at that rate.
Yeah, I think the environment is continuously changing, but your sensing and making sense of that environment takes 200 milliseconds. So that's where the DP gets formulated 200 milliseconds. but I'm going to talk about it sometime later, that the goal was to actually recompute the optimal solution in 50 milliseconds. So you want to make sure that you have some time to implement the optimal control. And yeah, so that was the problem. So even though DP is, you can't take 200. So generally in controls, you don't want to have delays. But if you're solving a DP, then there is inherent delay because you have to compute a DP. And so the goal is to always compute the DP at a much faster time scale than how quickly the DP gets generated. This one also there's perturbation because the vehicle. So it turns out, I did not know about it, but it turns out that as you change the speed of the vehicle, the HVAC systems energy consumption changes quite significantly. And so that was the goal, to use that information to improve the HVAC energy consumption. So this is the idea of, this is the pictorial description of what's happening. So you have this connected autonomous vehicle moving on the road. There is a whole bunch of pedestrians here who are crossing the road. And so that information will be streamed by some unit here, roadside unit here. And then these traffic lights are also streaming information that I'm going to be green for some time, and then I'm going to be red for some time, and then I'm going to be green again. And there are all these vehicles that are also streaming information about what they are going to be doing in the next few seconds. And so this vehicle, this is your autonomous vehicle with our DP. It needs to make sense of all that information and then recompute what the velocity of this vehicle is going to be as it navigates this signalized intersection. Another thing to note here is that this particular vehicle has a 48-volt hybrid, a 48-volt battery. So it's essentially a hybrid vehicle. It's not just an internal combustion engine vehicle. So there is some potential to manage the energy by moving energy from the engine to battery and battery to the powertrain. So all of that needs to be optimized for this particular vehicle, given all this information. Now, keeping this in mind, let's look at the HVAC of a vehicle. So this is the front of the vehicle, and this is the cabin. This is where the drivers and the passengers are sitting. And so the condenser is compressing the refrigerant, which is going in this particular loop. Oh, this is the compressor. So it's compressing it, then it goes through the expansion valve to the evaporator, and then it goes back to the condenser. And so as the vehicle velocity changes, the cooling property of this condenser essentially changes. And also this particular airflow, the velocity of the vehicle changes this airflow also on the evaporator. No, sorry, this one is the blower. So this is the internal fan of the car. So you can change the fan speed. So you might, as a user, you might change the blower speed depending on how hot or how cold you are feeling at that time. And so that changes, this changes due to the set point of the user or passenger, and this changes because of the velocity of the vehicle, and that changes. And the control actions here are m dot fan and omega compressor, which is the how much compression you are going to do for the refrigerant here, and what is the fan speed of this particular over the condenser going to be. And so then there are some states and there are some things that are environmental variables. So this one is an environmental variable, this one is an environmental variable, and that's changing because you are changing the velocity of the vehicle, and that's changing because the outside temperature of the environment is also changing while you are driving the vehicle. So generally speaking, if you're driving the vehicle between 12 noon to 4 p.m., the temperature doesn't quite change that much. But if you're driving the vehicle in the morning, then the temperature changes quite rapidly between 7 a.m. to 8 or 9 a.m. So this particular temperature, ambient temperature, is going to change quite significantly over a 1 or 2 hour duration. Or if you are climbing up the hill or something like that, then again, some of these things change because the temperature as well as the air density would change as you are climbing up the hill or coming down the hill. So all of that information can be used to optimize the HVAC energy consumption in the vehicle. So how do we formulate this problem? So like we understand from a applications perspective what the problem is going to look like. So let's look at the model for a Markov decision process. I'm calling it Markov, but there is no uncertainty. I'm going to remove the uncertainty from the picture for the purpose of this talk. But you have a state space, you have an action space, you have state action constraints. Typically, the state action constraints would be in a form of a function of state and action, and you want this inequality to be less than equal to 0, this function to be less than equal to 0. You have a cost function, you have a transition kernel that looks at the current state action pair and comes up with the next state. And then you have a policy that you're trying to optimize from state to action such that the policy always lies within the admissible set. So if you think about the eco-driving example that we just talked about, you have fuel consumption and driving time. That's the cost function that we are trying to minimize. Vehicle dynamics is the transition kernel right here. And then the safety constraint is essentially this state action constraint pair. So we want to always make sure that the safety constraints are met at every point of time. Any questions so far? So this is the general setup, and we are going to make the state transition function deterministic in the next slide. So this is my finite horizon expected cost. I have the terminal cost, I have the running cost. My action is picked according to the policy. My state transition is picked according to the state transition function. And the way to solve this problem is to apply this dynamic programming algorithm, which is you keep track of the future cost to go, and you have the current cost, and you minimize the total cost, total expected cost over the admissible action set, and you get the current value function, and you sort of proceed backwards from capital T to time t equals to 0. Now, what happens while we are on the road or we are carrying out some mission? So I have my original nominal MDP. This is the problem that I just solved at this particular time step. And I have my pi star t and b star t, which is the optimal policy and the optimal value function. And then after 200 milliseconds or after 5 seconds or after 15 seconds or after 1 minute, I now have a new set of constraints. I have a new cost function. I have a new transition kernel. And now I have a completely new optimal policy and the optimal value function corresponding to this perturbed MDP. So the question is, I've already computed this. And after 100, 200 milliseconds or after 5 seconds or after 10 seconds, I have to recompute this thing all over again. And DP is a very compute intensive process, calculating solution. So how can we reduce the computation? That's the problem. So given that we know pi star and v star of the nominal MDP, how can I show, or can I show that the perturbed policy, optimal policy, is going to be the original policy plus some small perturbation? And can we compute this small perturbation using simple computation? So I don't want to do very complicated computation for computing the optimal solution.
So this is an idealized model of your actual problem, because if my true constraints were changing continuously over time, I would need to compute a robust policy rather than an optimal policy, because I want the constraints to be satisfied even if the parameters change within a policy.
You see, when you are driving the vehicle, you never have such significant perturbations without prior knowledge in a connected vehicle environment. So what I mean by that is, if a car is supposed to come into your lane, so we are not talking about accidents here. So if a car is supposed to come into your lane, it will first turn on the indicator, and the connected system within that vehicle will automatically broadcast that I'm going to come into.
No, but that is, I can also have constraints like, I mean, I don't know how an engine works, but let's say my compressor cannot actuate more than a certain torque or something, right?
That's right.
So if that perhaps depends on the speed at which you are going, or the speed at which wind is blowing, which is outside your control.
Yeah.
And depending on your sampling time, you will know that the wind speed could change within some amount during that time. So you may have chosen a control policy according to what the state was earlier.
Yes.
But if the function age changes over that interval when we're executing that policy,
Right.
then I may not be using feasible actions.
I see your question. Okay. So there is a hand wavy point and then there is a mathematical point. So the hand wavy point is that even if you miss the constraint for a few milliseconds, it doesn't really create a problem. It creates a problem in the DP because now you have infeasible action. In reality, it doesn't really create a problem because the systems are designed in a way that even if you have infeasibility for a few milliseconds, you might have higher emissions, you might emit more carbon dioxide than you had intended at an overall level. And so that doesn't really affect your, it doesn't lead to an accident, right? So that's what happens. This is something that we had thought about at that point of time, and we realized that actually just having slight infeasibility is not a problem as long as you are pretty much feasible throughout the drive cycle with 95% of the time or 98%.
But in the case of your vehicle moving into your lane, that is different though, right? Because
yes,
because
and
you
that
have
only
to reduce your speed significantly, otherwise you have a crash.
exactly.
So you may not have enough time if you're going too fast to do that.
Actually, you have enough time because that vehicle is communicating that information to your vehicle in this setting.
No, but then the robust thing is better there, right? So I wouldn't go to a high enough speed that's where I would, so my solution would try to maintain that, the fact.
Correct.
The robust thing would be, the constraints would still be met when you're going further up.
So what happens when we are driving on the road, right? So if a vehicle has the indicator on and it comes, so let's assume the case where the indicator is on because that's how we understand that.
Then you start braking ahead of time, right? So
you start braking ahead of time.
So then you're trying to meet the constraints, keeping the
exactly.
You never violate the constraint.
You never violate the constraint. So because your DP senses, as soon as you turn on the indicator in 200 milliseconds, the DP knows that now that particular vehicle is coming into the lane. You know what the vehicle speed is at that point of time. So your vehicle speed and that vehicle speed has to, like the constraint on your vehicle speed changes from, let's say, 70 miles an hour to 65 miles an hour because that vehicle is at 65 miles an hour and it's coming into your lane. And of course, the distance constraint you will violate for the first few milliseconds. You will, let's say the distance is supposed to be 20 meters, but instead you are at 15 meters. So you will violate that constraint for maybe 5 milliseconds, I mean, whatever, 1 or 2 seconds, but then after that, you will start maintaining that. So DP will take care of all of those. That's why you are computing it every 200 milliseconds because you get all that information.
I think you may not even, if you go to 70, you may not even have enough time to.
I mean, we drive all the time. It's...
No, but you also have accidents all the time. So,
so the accidents happen if one of them is distracted, right? But in this setting, because it's a connected autonomous vehicle, arguably it's never distracted.
Oh, I feel that you need to have the robust solution there, those cases, because then you go to like 67 as opposed to go to 7.
Right, but that's still a constraint, right? So that's part of your DP. If you're robustifying by just changing the constraint of the system, that's completely fine. All I'm saying is whatever constraint I had, whether it's 67 miles an hour or 70 miles an hour, that constraint gets changed because.
Actually, I had a different question. Is this a valid objective? I mean, when you say pi star is your optimal policy.
Yeah, for the nominal MVP, the one that you've already solved.
And you think that there is continuity in the pi stars in some sense? So
I'll show you, yeah. Under some condition, there is continuity.
Well, essentially, you need unique policies and unique.
Absolutely, absolutely. Yeah. You need second order sufficiency condition.
If you're going for suboptimal policies or very close to optimal, then you could have continuity.
Yeah,
that's better to assume.
Yeah. So I'll go into the derivations of that. Wonderful. So this was my original MVP, and like I said, I'm not looking at transition kernels that are stochastic. I'm looking at kernels that are deterministic. So I just have the typical state transition function. And now I have the perturbed optimal control problem. So I have the original cost plus epsilon times this change in the running cost. So my set point has changed. So imagine if you are in the vehicle, you're very hot and you change your vehicle set point temperature from 22 degrees Celsius to 21 degrees Celsius. Or if you're cold, you change it from 22 degrees Celsius to 23 degrees Celsius. So now you have perturbed the tracking error. And so that appears in the tracking cost, in the cost of the system. And then you have perturbations to the constraint. And then you have, so for the first part, I'm going to assume that the state transition function doesn't get perturbed. But in the next part, I'm going to assume that the state transition function gets perturbed as well. So right now, let's, for the sake of simplicity, assume that the dynamic remains unchanged. And this class of problem is, so this framework is very similar to the frameworks that have been pretty classic within the controls community. So ILQR, DDP, differential dynamic programming, and sequential action control. All of these are different frameworks that are used to solve problems of this type under various settings without the constraints. So typically in the traditional robotics literature, they tend to ignore the state action constraint, or they have just a box constraint on the action. But we are assuming nonlinear state transition function, nonlinear constraint, and then nonlinear cost function. So we differ in our approach in comparison to some of these existing tools. So the existing tools are trying to solve this problem optimally, whereas we are trying to solve the problem with perturbation and perturbed constraint, but with complete nonlinear system. But these are all differentiable. So it's nonlinear, but these are all differentiable functions, so that I can compute the first and second order derivatives. So how do we solve this problem? As I mentioned, at every point of time, I'm going to be solving this constraint optimization problem. And the hope is that in the perturbed problem, I'll have the original nominal cost to go function, which I had computed at the previous time step. And then I'll have some first order perturbation and then higher order perturbation term. And so what we are going to do, just in a nutshell, what we are going to do is, this problem is something that we have already solved. This is the perturbation at every point of time that I need to solve for. And then I'm going to ignore this higher order terms, and I'm just going to solve this first order extension of the DP at every point of time. So that's roughly what our goal is in the rest of the talk. So under various smoothness assumption, this is all second order sufficiency condition for solving constraint optimization problems. So assuming that the second order sufficiency condition is satisfied at every point of time and at every state action pair, which is a very strong assumption. But in most of these practical problems, these assumptions are satisfied, barring on a set of measure zero, which are the boundary conditions where these conditions are not satisfied. But rest of the state space and action space, these conditions are generally satisfied, except for on a set of measure zero. So under this condition, the perturbed policy is the original policy plus epsilon times first order term, and then some small o of epsilon term. So you can actually show that the perturbed policy is differentiable in epsilon at epsilon equals to 0. And this dt term can actually be computed by solving a quadratic programming problem, which from a vehicle's perspective, solving a QP is much, much easier than solving a very complicated nonlinear optimization problem.
You should look at some of the economics literature. They deal with all of this stuff most of the time. I mean, you may have fewer conditions than this.
No, I think these are fairly general conditions. You have to apply implicit function theorem to prove that there is this optimal solution is differentiable with respect to epsilon.
Something similar for looking at, I forget the exact term that they use for tracking how equilibria change with parameters.
That's true. That's true. Exactly.
So smaller, you may not need all these conditions.
That's right. That's right. Yeah. I know there is a paper by Asimoglu on how the equilibrium changes. And there are many papers.
Real strong stuff.
Right.
So, sorry, wouldn't you need some kind of a projection step here also to ensure that the new policy remains feasible?
I'll get to it. There are only a very corner places where these infeasibility occur. And so you need to then put in those constraints in order to make sure that those infeasibilities are taken care of. That adds slight complications to the DP, but it's still better than solving the entire DP all over again. So let's look at a simple problem, which is a quadratic optimization problem, such that you have some equality constraint. And what I want to demonstrate is why is this theorem correct? Okay, or can we see that that theorem is correct in the context of a problem that we know how to solve? So how many of you have taken an optimization class before? Okay, a few of you. Okay, so this is the typical quadratic problem with equality constraint. Assume that A is full rank and H is a positive definite matrix, and this is just the usual vector. And so using Lagrange multiplier theory, you can actually solve this problem exactly, and your Z star is given by, the optimal solution to this is given by this expression, where kappa star is the Lagrange multiplier, and that's given by this particular expression. Now, I'm going to change the cost functions a little bit. I'm going to change the constraint a little bit. And let's see what the optimal solution of this looks like. So there is this famous result in the linear algebra, which is Taylor expansion of matrix inverse. I did not know about it. So while solving this problem, I learned about it. And now it's my favorite theorem for the last 5 or 6 years. So essentially what happens is you have a matrix, you perturb that matrix, you take the inverse. This is the Taylor expansion of this particular problem. So this is equal to the matrix inverse minus some term plus the higher order terms. So you essentially see this particular pattern emerging with epsilon square, epsilon cube, epsilon raised to 4, and so on. Okay, so that's the Taylor expansion of the matrix inverse. And now I can substitute that expression here. So whatever expressions I see here, I can substitute that here with that that Taylor expansion of the inverse, and I come to the following conclusion. If my Z star equals to 0, then a lot of terms cancel out. So if my Z star is equal to 0, then Z epsilon star minus Z star is epsilon times the correction direction plus some small o of epsilon term. So this small o of epsilon term appears here. And then you have the first order term that leads to this complicated expression. You can also compute the change in the Lagrange multiplier, which depends on E tilde and B tilde, and M is given by this particular expression. Okay, so one thing you note here is that this optimal solution, Z tilde epsilon, is actually differentiable in epsilon, as you can see, and this is consistent with the main theorem. Okay, so this is the core result. This is the result that allows us to extend that DP over the entire state and action space. So what do we do at every point of time? We compute the H, E tilde, and A matrices based on the active constraints, based on the second derivative of the cost function and the second derivative of the value function evaluated at the current state transition function. And this V tilde is my update to the estimate at the next time step. And so that comes under the E tilde term, and then V tilde is whatever changes in the constraints that you see. So your velocity constraint might change, your distance constraint might change. So how do you incorporate all of that in this particular term? And then you can compute the first order change in the optimal policy and the first order change in the value function using the expressions given here. And it's not important to understand every part of the expression. It all follows from the previous result. But what is important to note here is that all of this is matrix multiplication. So if you are in a embedded hardware on a vehicle, you can actually implement this algorithm much, much easier. The only problem is how are you going to get this second order derivatives? And the point is, if your problem is a tracking controller or uses simple function approximators, then even these derivatives are easy to compute, and therefore you will be able to have these expressions within your memory. If not, then you will have to recompute these second order derivatives every few seconds or every few minutes or every few hours, depending on the problem. But the computation of the second order derivatives is something that we don't worry about in our problem statement. We just worry about the computation of the optimal solution or near optimal solution with a note that in some cases, these derivatives will either be computed, will be offloaded to the cloud. In some cases, these derivatives will be easy to compute within the vehicle itself. And if you are in the most general situation, then of course, computing these derivatives becomes a problem. But you anyways have to compute these derivatives to solve the DP problem. So you're just using that derivative, you're storing it in the memory and reusing it every few minutes or seconds.
Just a follow-up on that.
Yes.
I think so you're assuming implicitly with the active constraints.
That's right. That's right. Because that's our assumption. So I can do that. In reality, of course, there are, anyways, yeah. In reality, I'll show you that there are very small regions of the space where these constraints are not met. And so you have to solve the QP in that case. So you'll have to have all the constraints, not just the active constraints. Now we are in the situation where we are trying to optimize the HVAC system, and you have these parameters, which is the velocity of the vehicle, which is external to the HVAC system. And you have the ambient temperature, which is whatever the air temperature outside is, which is also external to the HVAC system and not controllable. But these are things you can measure. You can measure the velocity of the vehicle. You can measure what the ambient temperature of the air is. And so you have this HVAC energy optimization problem subject to constraints and the state transition function. And then you have this perturbed problem. Your parameters shift by some delta t, which is an update to the forecast. So I'm driving my vehicle on the road. Suddenly it became from green light, it became a red light. Now I have to stop my vehicle at the red light. So my velocity, instead of being 30 miles an hour, became 0 miles an hour. So that's the update in the forecast. And now my cost function has changed, my constraints have changed.
So you're assuming you know the trajectory of theta for the next capital T?
Next 5 seconds, next 4 seconds, something like that. Yeah. Or you may be on a hilly area, hilly terrain. So you might be either going up or going down. So I don't know if any of you have driven in the mountains, but one thing that I've done on the mountains just for fun, because I'm an optimizer, so I have to do it. When I'm going uphill, I turn off my AC, but when I'm going downhill, my AC is on full blast. Okay, so very low temperature and very high fan speed. And so the AC actually slows the car down when you're going downhill. So this actually happens. You can test it out yourself. And that way you can optimize the energy consumption of your vehicle. I did that at Yellowstone National Park, so I remember that day very well. I was very excited and very happy that I was able to optimize the energy consumption of the vehicle. And I didn't have to use my brake. Okay, so my air conditioning system was actually stopping the way, making sure that I'm under the speed limit when I was going downhill. Anyway, so you can then apply the parameterize the optimal control problem that we just talked about. You can apply the WASP algorithm and you can solve this problem. The reason I'm not going into the details of this particular algorithm is because the expressions are horrendous, but it definitely works, and I'll show you the numerical result. So this is the first part of the problem where I'm doing velocity tracking. I have a very small perturbation to my velocity tracking problem. And so the red curve is the WASP, the output from the WASP algorithm. The blue dotted curve is the perturbed DP solution, the true solution of the perturbed DP. And the black dashed line is the true solution of the unperturbed DP. And so around the tracking velocity, it doesn't really change much, but towards the edges, you will see that the three solutions or three value functions are quite different. So this is the value function, this is the control strategy. And so they are quite different towards the end, but very close to each other in the around the velocity that you are trying to track. And here you see, what you see is that the constraint of the perturbed problem and the unperturbed problem is essentially the same in this particular region. It is the same in this particular region, and it is the same in this particular region. There's only small area here and a small area here where the two constraints are changing. And that's where the problem appears, because the set of active constraints of the vehicle changes. And so in these regions of the state space, you have to solve the entire QP. So you apply WASP algorithm, you look for infeasibility. Wherever there is infeasibility, you redo the computation with the full constraints. Otherwise, you just let the solution be, as long as it's meeting the constraint. But you can see that the WASP solution actually sits between the unperturbed problem and the perturbed problem. So we are in a very good agreement with respect to the theory. This is a situation where epsilon is equal to 1. So you have a huge perturbation in the cost function as well as in the constraint. But we are able to solve the problem. Again, in this particular region, the set of active constraint is this is the state. So in this particular region of the state space, the set of active constraint has changed quite significantly. So you have to solve the entire QP. But in this region and in this region, you don't have to solve the entire QP. You can just apply our WASP algorithm and you will get the near optimal solution.
Sorry, just
Yes.
so when you say in the top graph, when you say perturbed dp, that's the optimal value function of the perturbed dp.
Yeah, this is the optimal value function of the perturbed dp.
And the unperturbed dp is the optimal value function of the unperturbed
dp.
So wouldn't it be more sort of interesting to also compare what happens if I use the optimal policy of the unperturbed dp in the perturbed dynamics?
That is the current state of the art. That's exactly.
Yes, but sort of what its performance is.
I mean I see. Okay.
Right? Because WASP is an improvement over doing that, which is
Yes.
the dumb thing.
Yes. I haven't checked the performance. We did not do that. Yeah.
Okay.
But I guess that's a good point. It probably would lie somewhere in between this red curve and this.
Yes, right?
this
Hopefully.
Hopefully. Yeah.
Right, because you haven't really shown that
Yeah.
you are better than.
That's right.
I mean, in principle, you should be, because you're taking a step
Correct.
in the direction.
Correct.
So, but that's the objective you should be.
Yeah. The only issue is that you will be infeasible.
But that should show up in your value function, right? If you become infeasible somewhere, the value function should blow up.
Not quite, because value function is the cost to go. It doesn't have the constraint.
I mean, depending on how you.
Right. So we'll have to then add a constraint, something like
He's not looking at the Lagrange. So.
No, but if it depends, right? How you model a system in which I take an infeasible constraint, you can say I get a huge penalty.
You can do that, yeah,
Right.
definitely, yeah.
But the or you can take the old policy and just make it, don't take an infeasible constraint, because you have to do that in,
Right.
there's some projection happening
That's
in
right.
our case also.
That's right.
So
Yeah.
if, just the action prescribed by the policy, project it onto the constraint set.
Right.
And take that action, so it is
Right.
infeasible, but
Yeah.
performance would be,
Yeah.
if I had not changed versus if I
Yes.
take a step in the direction.
Yeah.
Because intuitively, I would expect that when epsilon is small,
Mhm.
not changing is also okay,
It's definitely okay.
right? Because your
Yeah.
error is or little o of epsilon.
That's right.
Right, so it's
That's
only when
Correct.
epsilon is big
Correct.
that doing this recomputation is
Yes.
significantly.
Absolutely, yeah. So,
You have implicitly assumed that your conditions are such that the optimal policy is closed. So
optimal policy is closed.
that's what you should get pretty much.
Yeah. Very similar. I mean, same thing in the sense that it will be somewhere in between the two, as long as.
Don't exactly know where it is, but yeah.
Yeah. One other comment that I wanted to make here is, suppose that you applied WASP once and you got some result. It turns out that you can apply WASP again. If you're not very happy with the result, you can apply WASP again and you get much closer to the optimal solution. So this is the one application of WASP algorithm. You can apply the second application of WASP algorithm and you can be much closer to this blue curve. And you can be much closer to this blue curve here. So
is there a theorem there?
it's not there, but we observed it in practice. So if one WASP is if the update, if dt, so going back to this expression, if this dt is very high, you can apply additional WASP. So you get like the second term as well. So additional WASP at this particular new policy and new value function, and you get a much better approximation. So this was the question that was asked in GE because they have significant perturbations in their operating condition. So they were saying that if one application is not good enough, then what happens if you do another application and then we check, then you get much closer to the optimal solution. So about the computation time, so you have the perturbed DP, you won't start from the nominal solution, which is pi star and v star. It takes about 2.87 seconds to solve that particular problem. This is on MATLAB on a computer, so certainly the code is not optimized to solve DPs, but this is using fmincon within MATLAB to solve the constraint optimization problem. So this is what the baseline solution is. If you use only WASP and you don't do any further computation, you get 80% speed up in the computation time. And if you use this particular output to warm start the perturbed DP, you can actually solve the problem much faster. And overall, you get 15% reduction in the computation time with respect to the baseline, where you are warm starting from the nominal solution. So that's
more than 2.87.
yeah. So, but you need to add this particular term here.
In addition to that.
Yeah, in addition to that. This takes 1.85 seconds.
I thought that 1.85 included the 0.6.
Yeah, no, it does not. Yeah.
Okay, then
It's just a problem of me being able to create this figure.
okay. Yeah, otherwise, then
Yeah.
I can say 15%.
Yeah.
Otherwise, it's almost
Right.
more than 40%.
Right. We were able to implement this algorithm in the vehicle, and we demonstrated that don't go by this 30%. This 30% reduction in fuel cost was on some specific drive cycles, but on an average, we were able to get 20 to 30% reduction in the fuel efficiency by using a variety of technology. But the only reason why this algorithm was useful is because we were meeting the safety constraint, what is called functional safety requirement of the vehicle, by recomputing the DP within a matter of 50 milliseconds instead of 200 milliseconds to solve the DP on the hardware in the vehicle. So one thing that I always emphasize for optimization algorithms is if you're implementing it on embedded hardware, then you are truly constrained by the computational environment. And so you should always be cognizant of the fact that your algorithm should be able to execute on the embedded hardware within the time constraint given by the functional safety requirement of that particular system. So we were able to meet all those requirements for this connected autonomous vehicle. We did the actual run on a test track around OSU. So but I don't have those videos and stuff. It's something that mechanical engineering faculty colleagues show in their presentation. For the thermal management in electric vehicles, we were able to apply this WASP algorithm, and we demonstrated that we are able to solve the problem in a matter of 25 seconds, whereas perturbed DP would have taken 120 to 130 seconds to solve. So we were again meeting the requirements, 80% reduction in the computation time without much loss in optimality. So this is the unperturbed DP cost associated with set point. This is the WASP cost associated with the set point. So you can see that this cost, the perturbed DP cost and the WASP cost are very similar, but very different from the unperturbed cost in some of the cases. So this also shows the trajectory, the state trajectory over time. So this is the time axis, this is the state, this is the state, and state. And you can see that the blue is the unperturbed problem, the red is the perturbed DP solution, and the yellow is the WASP solution. And you can see that the WASP solution nicely tracks the solution of the perturbed DP over most of the time, except for there are some situations where it does not. So this is, of course, the state trajectory, not the action, but actually compressor speed is the action. Condenser pressure is the state, air mass flow is the action. evaporator pressure is the state. These two are states, these two are actions. So you can see that WASP is in good agreement with the perturbed DP solution most of the time. So we are trying to extend this this whole theory of perturbed DP to generate new kinds of reinforcement learning algorithm. That's the joint work with Aditya, and we've been working on it for over 2 years now. We needed to use a lot of functional analysis in order to come up with the algorithm, but now we have a very solid reinforcement learning algorithm where the state action spaces are Polish spaces, the policy space is viewed as a linear operators over function spaces. And we're able to come up with new class of algorithms which are distinct from the PPO and TRPO algorithm for solving reinforcement learning problems. Through simulations, we have shown that this is faster than PPO for finite MDPs, but for general MDPs, we are still continuing to run the simulations. The applications of some of these newer algorithms are in discovering solid electrolyte or discovering materials or doing flow control over rigid bodies. So these are the kind of problems that we are currently thinking about and looking into, where some of this perturbation theory things that we talked about today could be very useful in real world implementation. So to summarize, we have an algorithm, WASP algorithm, which is 80%, around 80% faster, or 79% faster than solving everything from scratch, solving the DP from perturbed DP from scratch, which has also led to new RL algorithms that I did not talk about today, but I'm happy to chat about it offline. If you're more interested in optimization, linear systems, reinforcement learning, and so on, controls topics, all my courses are on YouTube. You can like, subscribe, and share my YouTube videos on this. And I really want to acknowledge my co-authors who are now employed in various companies around the country, and the funding agency, RPI, which supported most of this particular work. So thank you so much, and happy to take questions.